Yeah, thank you for having me, Michael. And thank you everyone for coming to the talk. So I'm going to talk to you today about some work that my friend Carl and I have done. We call it the Mortal Computation Thesis. And I think it complements some of the things that I know Michael's group does. Actually, in fact, we cite particular mortal computers that I will get into a little bit later, and we can talk about that perhaps. So just very briefly, who am I? So I'm Alex Ororbia, and I'm the director of the Neural Adaptive Computing Laboratory at Rochester Institute of Technology. These are my students, as you can see, and we work on quite a few things, but our primary focus is building biomimetic systems and the learning algorithms and computational architectures that would facilitate their learning and inference, with the goal of obviously building things in hardware substrate. So again, neuromorphic computing might be familiar to some of you. We also work on a lot of things based on the free energy principle. Some of you might have heard of predictive coding or active inference, and my group contributes to that. And we have a lot of collaborators, but this is just our brief little intro. So you might be asking, what exactly is mortal computation? And if you're familiar with it, you might be aware that Jeff Hinton last year came up with a phrase called mortal computation in one of his works, the Ford algorithm paper. And the idea effectively is that software cannot be divorced from the physical substrate or hardware in which it is instantiated. And the idea is that the calculations and processing are embodied and in fact inseparable from the medium. The medium, when the medium breaks down, stops functioning, the software ceases to exist and cannot be carried out on another medium. This sort of effectively says that the software should die along with its quirks and its properties if the hardware or substrate that executes it ceases to function. And of course, this is going to have implications for edge devices, energy efficient systems and robotics, and so on and so forth. However, this challenges the notion of immortal computation in computer science. It's sort of a foundational idea that we can essentially write our program independently of the medium that we're going to execute it, and that this program or software can be copied or executed on another GPU or TPU server, for example, if you're doing machine learning, and it's going to pretty much run the same. It's not going to have any particularities that are tied to its actual medium. And so effectively, the knowledge and characteristics that your program acquires is done irrespective of the medium in which you are executing it. So this is the work that maybe I believe you were linked to. It's a little bit long, so I don't blame you if maybe perhaps you didn't read it all. But this is work that we sort of did like a review and then sort of a perspective on what mortal computation really should be, as Jeff sort of just introduced it in about a couple of sentences. So Carl and I wrote 40 pages roughly about it. So why exactly mortal computation? Well, part of it is a thermodynamic consideration, and this is basically getting at the relationship between information processing and thermodynamic efficiency. The idea effectively is that we want to adhere to Landauer's principle, and these are just some principles I'm going to briefly introduce. Those of you who might have a deep physics background might even understand them even better than myself. But the idea is that there is a minimum amount of energy required for any irreversible operation. Think of like erasing a bit on your computer, and it is proportional to the operational temperature of the computing system. And I just give you the relationship here. KB is Boltzmann's constant. And the idea is that an irreversible change in a computer's stored information requires dissipation of a minimum level of heat to the environment. This is paired with the Jarzynski inequality, and I have a floating bullet point there, but that's because I wanted to remove some unnecessary detail. But the idea is that we're talking about the difference of the free energies, the physics free energies between two states, X and Y, and we are saying that the difference between them can be constrained to be equal to the average of the work, the physics work done from all paths taken from perhaps an equilibrium state X to a typical non-equilibrium state Y. What does this really mean in plain English? Well, roughly we can know something about a system's equilibrium by observing the system when it is not at equilibrium. And so the main takeaway when you pair these ideas together, as Carl and I argue, is that there's a lower bound on the amount of thermodynamic work that you need to do to change information content in an information system. And so this, of course, has wonderful implications if we can get our intelligent systems that we try to strive today in artificial intelligence to emulate, to build something that adheres to in-memory processing. And effectively, this just means that we are changing the computer's information content, and we are saying that it's equal to the inference belief updating in response to external perturbations. So as the computing system is dealing with an environment, we essentially want to be working at as close as possible to the substrate. These calculations should not be divorced. And then, of course, we can tie this, as I'll show you a little bit later, to the variational free energy formulation. And effectively, that when a computing system or an intelligent system is minimizing its variational free energy, it's the same minima as the thermodynamic free energy, and there is equivalence in work that we point you to. And so, of course, the idea is that we need to essentially try to circumvent what's called the von Neumann bottleneck, or the memory wall. And that's the idea that when we are doing things, you might be aware of deep learning and what is rocking the world of artificial intelligence to this day. We're effectively executing our programs on software that is in random access memory. And as you can see in the bottom left diagram, there's a lot of expended energy to start moving information from long-term memory, depending on your computing structure, to random access memory. And so we essentially would like to overcome that. And that's sort of what just one common example that we see today in memory computing is neuromorphic computing, where we're effectively designing our biological models, our neuronal models, actually as close to the hardware as possible, and using things like memristors to adhere to synaptic connections and so on and so forth. But ultimately, the idea is that realizing thermodynamic efficiency of Bayesian computations, which is effectively what biological systems we are doing, requires belief updating in memory. To be Bayes optimal is to be thermodynamically efficient, and vice versa. This also has some wonderful implications for green AI, which is this argument that we need to essentially figure out how to do the intelligent operations we do today without expending mammoth quantities of energy. ChatGPT and transformers themselves are pretty expensive. So then there's also cognitive philosophical motivations. I won't dwell too long here as well, but the idea is that there is in cognitive science the embodiment thesis, or the embodiment hypothesis, and enactivism, which is just effectively saying at a high level that the mind, your mind, or any mind, is grounded in its sensory motor coupling. So the idea is that we are shaped by the actions that we take. The nature of mental activity depends on your body. Effectively, you need to be in some type of actual physical instantiation. You cannot have what is known in classical cognitive scientists known as brain in a vat. So the idea is that we don't have something called isolated cognition. We are actually primarily driven by our body. And enactivism takes us an extra step further. And the idea is that we are dependent on our environment. Our cognition is, we are coupled to an environment. We act, and effectively that affects us as well as affects our environment. So a mortal computer, in effect, is an active participant in the generation of the information that it processes, thus shaped by the consequences of how it acts and has acted on its niche. Effectively, this is called niche construction. And then we also talk a little bit about some other nice connections in naturalist philosophy and existentialism. That actually refers to a little bit the initial quote that you might have seen in the paper by Soren Kierkegaard. But the idea is that there is a finitude to life. It endows us with purpose, entails reproduction, and motivates us to pass on knowledge to future generations. Ultimately, death is a horizon that shapes our behavior and consciousness. Now, of course, while mortal computation doesn't go as broad and as far-reaching as existentialism and other aspects of natural philosophy does, it does actually, we do pull or extract a small part of it. Talk about that even animals in any organism is implicitly constrained and conscious, or maybe not conscious, of the fact that they have a finite horizon and they act accordingly. And then, of course, there's some other parts that we touch on in our framework about operational closure, which is just the idea that the system must undergo autopoietic self-assembly and self-maintenance to keep separate its internal states from its external states. This is going to motivate the Markov blanket construction of the mortal computer I'll talk to you about later. And then, of course, the idea of sense making, which is that there's a mutual dependence between external processes and an entity, whether it's a biological organism or rather any mortal computer, as we generalize, because a mortal computer does not need to be artificial. We are all effectively mortal computers. A biological system must distinguish itself from its niche, yet be coupled to it in order to persist in that niche. And this will motivate the idea that we don't want to dissolve in our heat bath. We don't want to cease to exist. So effectively, a part of the work that, again, you might have read is it's a review. This idea is, interestingly enough, echoed for many, many decades across all kinds of thinkers and engineers, and wonderful ideas have cropped up throughout time. So we sort of unified them and scoped them out. Obviously, this talk, given time constraints, is not going to possibly go into all the details, but I will give you a swath. So sort of you can think of the paper or the concept in terms of three particular slices. That's why it's called the three slices of mortal computation. We have a biophysics, physiological, naturalist philosophies interpretation in the top left. Towards the top bottom left, we have a cybernetics interpretation and then a cognitive science interpretation. And I'm going to give you some of the highlights. So we're going to start with the biophysics aspect of our framework. And I'll just leave this diagram to sit here as I explain just a few of the key concepts to sort of parse it. So the idea is that a mortal computer self-organization constitutes its thermodynamic and metabolic efficiency, and we talk about metabolism and autocatalytic closure as some motivating concepts, but effectively these ground the mortal computer's agency or its ability to adapt. Ultimately, we need to understand that a mortal computer is not at thermodynamic equilibrium, and it operates as a dissipative system, given that energy and matter would be lost by essentially, and the idea is that we are adhering to the first law of biological thermodynamics, which allows us to reconcile and ensure that we are still adhering to the classical second law of thermodynamics. Entropy has to increase in the environment, but in biological open systems, we don't see that. We see entropy decreasing. So the idea is you have to kind of view it all as one big closed system. You need the environment and the entity itself. But ultimately, a mortal computer or any entity that could be considered one, its metabolic organization stands far from thermodynamic equilibrium. And so ultimately, it needs to forage, like any living system or any system, to continue to acquire new resources. This sort of motivates like that bottom level of the diagram. The metabolic processes are essential primitives. This is something that Carl and I chose as language to pull a little bit from cybernetics and bring it back into the biophysics interpretation. But ultimately, these are the foundational components of a computer or a mortal computer or any system arranged within a morphology, of course. And then, of course, we need homeostatic or homeohetic processes that live on top of it. This is our active regulation of those essential primitives. And the idea is that we have metabolic processes, as we discuss, reactions that use energy to transform materials into structures that then harness further energy to transform transport material, eliminate toxins or surplus material. And of course, this is sort of our way of keeping track of set points if we want to stay within a certain range or near a particular value. And so we need to be designing out homeostatic processes, which ultimately, by the way, you'll notice that there's these arrows for influence in the diagram. So all of these processes, in effect, should have some type of influence on their sensory motor action. This is motivated actually a little bit by work by Egbert and others on chemotaxis and talking about metabolic dependencies and the idea that action is shaped and driven by your metabolic function. Sometimes it can be entirely dependent on, only dependent on that, but we sort of generalize it a little bit to allow some design flexibility. On top of this, many of you are most likely aware of what allostasis is, but we also need allostatic processes because this is, instead of having error reaction or reactive processes, we have error correction processes as well. So this is what serves homeostasis or homeohesis, precludes future deviations to the essential variables. And then, of course, at the very, very top is our autopoietic autonomy level. And this is where we need to account for the fact that a mortal computer, if to be, unification of artificial as well as biological systems, needs to have the ability to make itself from within. It must continuously reproduce, organize, maintain the relationships between its parts. and as well as do this without external intervention. It must come from within. And of course, then we have the notions of morphogenesis, because the idea is that the mortal computer needs to persist longer than its actual physical instantiation of its components. So that means its actual organization or relations live longer, and that's its identity throughout time. This will also motivate the self-evidencing aspect of mortal computation, and it's continuously reproducing itself. And then, as I mentioned, there are sensory motor dependencies that couple this to its niche. So ultimately, what does this really tell you at the highest level? Well, that we need to essentially design our mortal computer system with the niche in mind. The niche cannot be decoupled or disentangled. We need to understand the properties of the niche as well. Again, some might be wondering from computational backgrounds, won't this make the system rather brittle because it's rather dependent on the body and the niche that you are designing? But that's sort of the point. The idea is that your behavior and your cognitive functionality is directly dependent on your physical instantiation and the environment or niche in which you live. So again, the organizational closure of the mortal computer, it depends, or sorry, that means that the mortal computer operates on the basis of self-reproduced structures. And, as I've said already, the mortal computer is autopoietic. And so this is where we have sensing, actuation, and we need to be modeling and essentially accounting for energy exchange and matter transformation. And so again, at the bottom right is our reinterpretation of the homeostatic dependencies of some good work over the years. So we just have that as a little, and it was called, we generalized and called it homeostasis dependent, but it was originally called metabolistic or metabolism dependencies. So now we can move on to what we call the cybernetics backend. And again, this could take a while, but I'm not going to dwell too long on it. Effectively, what I want to say to you is there's a couple of concepts that we can bring from classical cybernetics. It's sort of like the forerunner to aspects of computer science and certainly to artificial intelligence. But ultimately, cybernetics deals with this concept known as retroaction. A system must incorporate ends or goals into its means or mechanisms in order to ensure goal attainment is absolutely inevitable or almost inevitable. And so the system, essentially the question that characterizes cybernetics is, how can a system learn what it needs to know in order to act effectively? This gets into these notions of self-organizing systems, elementary parts, and local interactions with upward and downward causation. And we detail these a bit more in the paper and point you to plenty of references for all those details. But the idea is that the system is dealing with variety, and this is the central concept behind cybernetics. And you can see, as you see on the slide, it's the number of distinguishable states in a system state space. Another way you can interpret it is the degrees of freedom that a system has in choosing what state it will be in. This can be reduced via selection. And this leads us to sort of organizing. And another aspect of cybernetics is there's a lot of principles and laws. And so we tried to organize a couple of them into three central pillars that we felt were useful and complementary to the notion of mortal computation. So we organized them into, as you can see in the bottom, stability, regulation, and growth. And so effectively, stability is going to relate really nicely to homeostasis and homeohesis, as we discussed in the biophysics part of the talk. And the idea is that the system, ultimately, its goal is to reach a state of stability or ultra stability. And all this means is that it performs selections to cross state space to try to reach new states until it converges to a place where essentially it doesn't need to alter its part-to-part relationships. It sort of stabilizes, and ultra stability means it's found an attractor it really likes. So this is a good place for the system. It's very hard also for it to leave that particular state. So ultra stability is effectively, it's able to maintain its homeostasis. It keeps those variables near its set point. It has all that it needs to sort of stay in a good configuration. And then, of course, there's other principles like the principle of asymmetric transitions. And these are things that are characterized deeply in cybernetics. System in unstable configurations usually moves to stable ones, but not the opposite. And again, a system, as it rejects fewer states, as it reaches more stable ones, the variety decreases as the system becomes more organized. Again, it's sort of converged to a good state. You can equate variety with thermodynamic free energy, but the idea is that then the system does work, or it exerts its variation to reach those stable states. If it is stable, it's not going to undergo variation, and it's less likely to expend the energy to leave its current stable state. So then the other aspect, or the other pillars you can see on the right slice of the diagram, is growth. And again, we're not going to talk about all little sub-principles. Again, I recommend reading the work to see how they all kind of fit together. But the idea is that our mortal computer must be morphogenic. It maintains its continuity and integrity by altering aspects of its organization and structure over time. Morphogenic processes may also be triggered by environmental conditions. And then, of course, we have this principle in cybernetics of self-replication. This is kind of really important, something we don't really have in artificial intelligence systems today. System behavior is important that it results in copying or generating copies of itself. We do have some classical work like the von Neumann universal constructor. You might have heard of Conway's game of life, sorry. And the idea is that these are models of rules or rule-based systems that can show you how you have death and life in computational systems. And then another important notion is that reproduction in a mortal computer would not just be replication, but you would add mutation. So if we have perturbations to a replicated copy, now we have an offspring, and now that is subject to the same pressures that the original source computer is subjected to, and it will undergo selection and try to find its own stable states. Ultimately, then you can think of reproduction as another means to propagate one's identity through time. And then the last principle, or the last pillar that we organize, is cybernetical regulation. I do mention sometimes cybernetical homeostasis is kind of like implied throughout various principles, but we have the law of requisite variety. Just very briefly, what these three principles ultimately try to tell you is that you need to have enough internal variety in order to, or at least enough equal amount of internal variety compared to your environment's variety in order to successfully maintain, for example, homeostasis, or block particular variables and stay in a stable state, or more. You could have more variety, that's fine. So it is an inequality. But the idea is that this is important for a system essentially to try to maximize its internal variety in order to be optimally prepared for all possible perturbations or things that the environment could throw at you. The good regulator theorem complements this a bit, and it's just basically saying that every self-regulating controller of an environment must itself contain a model of that environment. And this motivates the notion of a generative model, that effectively one way you could think of it is that the mortal computer or entity is a generative model of its own environment. So the mortal computer ultimately seeks to become a model of the niche that it wishes to control. And then this motivates aspects of survival. And the principle of internal model control, I'm not going to go into it for sake of time, complements the good regulator theorem. It just basically talks about things that are how you deem if the system is structurally stable. And I'm going to move on because I want to make sure that I get through to the actual definition. So then the last slice that we review are, and we had a preview of this earlier, is aspects of cognitive science. So effectively, Carl and I sort of generated something that we called 5e cognitive theory. You might have heard of 4e cognitive theory, so we slightly extended it. Very briefly, if you look at the center component, the extended, embedded, inactive, embodied, and elementary, you'll notice elementary is the new aspect, or the new extension to cognitive theory. Elementary cognition, and I know many of in Mike's group is very familiar, it's basal cognition. And is that cognition stands on fundamental functions and structures that enable acting and tracking aspects of an entity's niche to ensure its survival. Finding food, avoiding danger, trying to reproduce. So these are, again, known as basal cognition, and it's a manifestation manifested through a system's autopoiesis. So this is sort of the base level that you must have as the starting point, essentially, to build a reasonable or effective mortal computer. And then, of course, on top of that lives the embodied cognition aspect. And this, again, they all depend on each other. So if you have one, you're going to start getting the others if you add these levels of complexity. So it's kind of organized as the higher up in this chain you go, the more complex your mortal computer is. Embodied cognition, as we talked about earlier, is that you can't describe your cognition or mental processing without a body. The idea is that you must involve the body or morphology of the living system. And yes, this is a little bit more of the extreme version of the embodiment thesis. There are a spectrum of different types, but we sort of leaned in more on the idea that we even offload cognition to aspects of our body. And this is motivated by like morphological robotics, where again, we know that if we can offload the physics onto particular limbs and things of that form, you can reduce the processing of the computational brain that you build into the computer. We know that inactive cognition lives on top of this, is the idea that you depend on your environment and you have a meaningful two-way relationship with it. Again, not only for extracting resources and transmitting waste, but you are essentially inhabiting and actively shaping your niche construction, as I mentioned earlier. Then on top of these, we didn't really go into detail. I'm just going to mention that you can get further and further more complexity introduced. You have embedded cognition, because the idea is that you live in a system of other mortal computers. So that's kind of what we have there on the left. We show some neurorobots as just an example. And the idea is that you are determined, your cognition is affected by cultural norms and other social interactions and the behavior of other entities that are also in this environment undergoing the same forces that you are. And so again, the mind extends now beyond boundaries of the individual. And then, of course, extended cognition is the final one, where you offload cognition, or the theory of extended mind, into non-biological or non-mortal objects. So if we generalize things to mortal computation, these are not mortal computers, like your pencil or your phone. So essentially, we are using objects as an extension of our cognitive functionality. And of course, that kind of like pie sliced circle is just sort of grouping them in another way. So we have basal cognition as like the biggest slice. It's more the foundational component. Morphological cognition deals with anything that would be bodily kind of cognition or processing. Inactive, of course, you need to account for the environment. And externalized sort of absorbs, extended, and embedded. So that was another way that we organized it. Some of you might have heard of Kirchhoff's life-mind continuity thesis. This is another way of saying like it's an artificial manifestation of it. So what now, equipped with all this review of wonderful work of far smarter people than myself, we get to the mortal computation thesis. So there are a couple of parts that I'll just introduce briefly, and I have reduced and cut away some of the mathematics. We can talk more about that if we want later. The Markov blanket is really the central underpinning of a mortal computer. And effectively what this does is this is our interface between what's inside you, or the entity, or the mortal computer, and what exists outside of it. It is that particular interface, and things are exchanged through that interface. We'll decouple it. We can break it down a little bit further. You could think of, by the way, a Markov blanket like a cell's surface, which separates intracellular from extracellular elements. And then, of course, we talk about sets. And again, these can be viewed as discrete states, but everything's really continuous and it makes things more complicated. But as you can see in the diagram to the right, we can decompose the Markov blanket into sensory states and active states. And these are the ways in which the agent actually gets information from the environment and transmits information to it, can do things to it. O is the external states of the environment, and Z is the internal states of the system itself. So these, again, are not observable by the environment, and the observable states are not observed by the agent and must interact through this Markov blanket formalism, or this construct. And again, this motivates, again, how you now need to design the body. You need to account for the morphology of the agent. And so here we have a little bit of a more expansion where, again, I told you what all the different ones are. We have iterators, and we talk about them as actual sets of states, and they evolve with time as well. So again, ultimately, what we want to take away from this is that there is a weak coupling in local interactions, and this will motivate the free application of the free energy principle shortly. And the Markov blanket provides that necessary partitioning. Non-living systems, by the way, that exhibit persistent local dynamics do not maintain a boundary. So you could argue, oh, well, this is your framework and the concept of the free energy principle. Markov blankets apply to a campfire, and the answer is no, because the campfire dissipates rapidly in the flux of the universe. It is extinguished by the downpour of rain. So this is not going to have persistent dynamics. It just has local dynamics, or you can think of a candle flame as well as an example of a system that would not be a mortal computer. So now we get to the idea that mortal computation, or the mortal computation thesis, is really just another corollary of the free energy principle. And just to briefly review what the free energy principle at one perspective is all centers around what I was already hinting at before, which is the non-equilibrium steady state solution, or the NESS. This is what agents or any mortal computer really wants to strive to reach. And so the idea is that, according to the free energy principle, or the FEP, entities maintain their structural and functional integrity by changing their relationship with their eco-niche through action. So action is really important because this is our way of which the system can actually forage for materials. So the free energy principle is about random dynamical systems that actively resist the natural tendency to disorder. Going to equilibrium and non-equilibrium is bad. That means you have died. And so the whole idea of mortality is we act so that way we do not die, that we do continue to persist. And then the free energy principle can then be broken down into kind of two key parts, as you can see with numbers 1 and 2. Mortal computers' internal density dynamics are conditionally independent of its environment. What does that mean? The environment and the mortal computer are weakly coupled, and the mortal computer has states that are distinct from its external or environmental states. That was, again, what was ZT versus O of T. And then the second key point, or the key aspect of the FEP, is that the mortal computer will continually self-evidence by returning to or trying to be as close as possible to its NESS, its nest state. So the mortal computer behaves to preserve its functional integrity, and its dynamics do not diverge when a perturbation is applied. So it's trying to gather those resources to continue to survive. It's striving to reach ultra stability, which connects back to the cybernetics backend. And then we talk a little bit about the formulation of the variational free energy. I removed all the terms for you for simplicity here, again, for the sake of time. But really, under the hood of the F, curly F, is that an entity has a morphology Q. This is referring to its actual structural organization. It has a set of internal states, and it has parameters mu. And so again, ultimately, the free energy principle is following the gradients or the differentials across each of those aspects. And we talk a bit more detail, but I'm going to shift you to the final piece of the puzzle, which is just, and we've seen this again implied throughout, morphic versus amorphic is an important distinction. We've talked about biological entities having a 3D physical structure, and von Neumann computers do also have that physical structure. They're designed to maximize heat dissipation and things of that form, but our programs and our software do not adhere to that structure. They are not entangled with it. They are not taking advantage of that. And so we have, again, in a morphic system, we have a thermodynamic cost and we have information coupling. These are very important constraints that characterize entities in this category. And so the morphology itself is a computational resource in living entities. We also go in the paper in the free energy principle about how you need to do structural optimization, which connects back to morphonogenesis. But our computers are our programs, our intelligent systems today, our software is independent of that substrate. Think of if any of you have experience writing a mathematical model for a deep neural network, you can write those equations independently of any realization of a 3D environment. The execution of that program is possible because of that computer's architecture, but you are not accounting for its morphology. It is amorphic, even though we present it pedagogically as dots and arrows and try to connect them back to synaptic structure. So ultimately, mortal computers follow the same self-evidencing principles as enduring entities. They are inherently morphic, thus we can apply or ground them in the free energy principle. As I mentioned briefly earlier, you can see to the far right, those are the gradient flows that you follow. And of course, we formulated them as differential equations or differentials that you could essentially traverse as the free energy sort of gets you back towards, or trying to minimize your variational free energy to get back to that NES. But this is essentially, we talk about the relationship between inference, learning, and structure, and how there is a circular causality between them. And we go at quite length, and I'm not going to go into in this talk because that's going to take a while. We also talk about mean field approximations and simplifications that give rise to known structures or neural structures in the brain. But the idea is that a mortal computer is a dynamics on structure with dynamics, was ultimately one conclusion that we lead. And we call this backbone mortal inference and learning, or MILS for short. And this is a key part of the final definition I'm about to show you. And remember that inference, changing or altering your internal states or variables internally, depends on learning. And of course, learning depends on those internal states. And then there is another interesting relationship we point out, that the morphology or the structure depends on the learning or the synaptic parameters, if we're thinking about neuronal networks, and vice versa. So there are these causal relationships or these circular dependencies that are necessary and actually important to embrace, that a lot of modern day machine learning or artificial intelligence does not embrace. And we should be looking to biology and neurobiology for those sources of inspiration for design. And I also mentioned that mortal computers are an instantiation of physically realized Bayesian efforts. Now, I'm not going to read to you this entire definition, but this is effectively one starting point, an informal definition of mortal computer or mortal computation, and what it would mean for designing this going forward for artificial general intelligence. Very briefly, the core agent goal is to remain in non-equilibrium steady state of stability in the face of a changing environment. Very briefly, from the high-level view of this definition, you will notice that it emphasizes strongly you need to have a morphology. Although we give you sort of a backdoor for those that do computational modeling, perhaps a virtual morphology would be acceptable for now. And then we obviously need to have accounts for homeostatic, homeohetic processes. So a generalized homeostasis or homeostasis. We also need to ensure that we have implementation of various aspects of MILS, as I just briefly discussed earlier. And then we end by talking about categories of different types of mortal computers. And we came up with some very broad, and these are subject to change because this is sort of pointing in a completely new direction for artificial general intelligence research to go into, or biomimetic intelligence. So we have homeostatic mortal computers, and they satisfy essentially the core principles of the definition, but in a very basic sense. So it has homeostatic regulation over those essential variables or primitives I mentioned very early on. You also then have higher level regulatory processes, so allostatic mortal computers. These might evince homeostasis in contextualized by allostatic regulatory processes. Obviously, the ultimate goal is to have a fully autopoietic mortal computer. And we actually already have some of these, interestingly enough. I'm going to wrap up with those examples, some of which Mike's group definitely knows for sure. And of course, we need to evince homeostasis, allostasis, and engage in self-repair and self-replication. So what, you might ask, do any mortal computers currently exist? We already have some of them. Not necessarily that the problem is solved, but rather we have some wonderful examples that we could bring back to the sciences of the artificial. One of the earliest ones is Ashby. Ross Ashby is a very important founding figure of cybernetics, which was one of the slices that Carl and I reviewed earlier. And Ashby's homeostat, which is what's shown in the picture here, is one of the earliest examples of what we would consider a homeostatic mortal computer. It's very, very simple, but it is able to stay autonomously in its own stable state. So it's able to maintain a form of homeostasis without any external intervention, and usefully enough, if you read into the literature, without any knowledge on the designer's part of really how this even works, which is kind of interesting. So the primary aim is it keeps its control variables within certain ranges. And we'll do this with random exploration. There are modifications that were done over the decades to add learning components to it. And then you can kind of make it look like what Carl tells me is an allostat. If you add some form of memory or learning, you sort of get a little bit more of an allostatic interpretation. The funny thing was, the homeostat can survive, as one comment from an early cybernetician says, something that any normal computer cannot, or digital computer, a wire cutter. You can turn off your normal computer and break it down, but a homeostat would learn to replace one of its submodules if you cut one of its wires, which is really interesting. Then we also have things by Pask and Beer, and many of those that contribute to what was known as maverick machines. These are actually variants of autopoietic mortal computers in some sense. The electrochemical ear was essentially a system made of several platinum nodes inserted in a dish. given an electrical stimulation, and they would grow and self-organize. You can also give them positive reinforcement, and that's why it was called the electrochemical ear. It would actually grow sensory organs in some sense that it could actually pick up sound waves. And it could build filters conducive to its survival. We also have fungal and mold-based computing. Some of them are designed based on or using, actually integrating the pink oyster mushroom, which is known for its internal geometrical calculations that can be reprogrammed. And then it can leverage the resultant electrical activity from the pink oyster mushroom to drive the actual circuits of the system. So you sort of get a chimeric hybrid type of system. And they have many useful properties that have aspects of autopoietic mortal computing, but not all of them. And it's not quite clear the current direction that fungal or mold-based computing will go, but it is a promising example of aspects of mortal computation. I don't need to spend your time on this one. I know you guys know xenobots quite well, but they are certainly an example of an autopoietic mortal computer. And, it's a swarm of biobots or biological robotic agents. Essentially, really, I'll just digest to the point of that they essentially exhibit a form of morphogenesis and basal cognition idealized in a multicellular form of a biological mortal computer. These could serve as a source of inspiration for in silico mortal computer designs as well, especially, for example, in neuromorphic computing. Maybe we could borrow a couple of the principles that we get. The nice thing about xenobots is they heal, which I think is the most important part. Yeah. And then there's some nice aspects about the hardware. And we talk about this in the paper and the extra appendix, that the hardware includes the genome, whereas the software is the cellular communication. The emergent cellular structures, and the software is the cellular communication that underwrites the creation of higher level structures. And then, of course, what was, let me see if I have it here. Why is it not showing up? For some reason, there it is. We also had very new recently, actually, we'd already finished drafts, Anthrobots, which are wonderful as well. We also have the organoid there to the bottom right, or known as intelligence in a dish. I also know you guys are quite aware of that, so I don't necessarily need to talk about sentient organoids. But these are examples of autopoietic MCs or mortal computers. And the idea is that they have aspects that strongly embody those central 5 tenets of mortal computation that we discussed earlier. And since I don't want to take up any more of your time, there's a lot of implications for artificial general intelligence. The mortal computation thesis could be one possible catalyst for what we think is the next stage of artificial intelligence research, where we need to go. A lot of today's work, again, from the artificial transformers you might have heard of, is that we have sort of centered around tool-oriented view or perspective of artificial intelligence. While it's valuable and stands to make a lot of nice benefits for humanity, the idea is that this is very different than how animals and humans, for example, conduct processing and how we are naturally intelligent. So we should be pursuing survival and its relationship to mind, and what that can teach us about embodiment and enactive intelligence. This could be the place that we need to go for biomimetics. By the way, bionics is just the engineering application of biomimetic intelligent concepts. And then we have some things, these are actually in the appendix, but I just wanted to briefly mention, we're essentially working towards like a form of artificial sentience rather than using the word intelligence. We are also not dealing with the questions of consciousness. We try to not really deal with that because that can get quite messy philosophically. That's not important for what mortal computation says we need to go, but there are some implications if we actually built the exact idealized mortal computer. Well, now we have the fact that they can feel, they can think. That do we have to consider giving them rights? And I think that's a wonderful and important ethical discussion that would need to happen, assuming that this research program gets built on. And then we have this problem called the body niche problem. Very briefly, it just means that, let's say research groups like myself, we don't have xenobots, we don't have access to organoids. So it'd be very hard for us to actually use those resources, unlike those in the biological domains. But perhaps we could build virtual morphologies. And we talk a little bit about how that's done in robotics, and that could serve as an example to democratize aspects of biological mortal computers. And so I'll leave here. I'm not going to blab about this slide, but I'll leave it hanging here. These are some questions that even I had as I was reading or rereading some of Michael's group's wonderful work about anthrobots and xenobots, and some potential interesting collaborative or at least directions that could be explored. And I am shamelessly plugging my lab software for modeling neuronal dynamics in biological credit assignment and so forth. So with that, thank you very much. And if there's any questions, I think we have like at least 10 minutes or so.
Cool. Thank you so much. Anybody else have questions?
I've got a question. So, yeah, thanks. This was really interesting. So back when you were talking about these three pillars of the cybernetics as they apply to this, I was interested in the growth pillar. Could you just expand a bit upon what that is telling us, basically?
Yeah, so, and I don't know if I have it here. Actually, it's good to look at the, actually, I'll do it this way, so I don't have to, yeah, the growth. Yeah. So there's a couple of more principles and things that I sort of hid here. Can you kind of see the slide, at least the picture?
Yeah.
So the nice thing about growth from cybernetics is the idea that, and I mentioned that, you know, one of the starting points is self-replication, the idea that you should be able to produce copies of subsystems or produce essentially duplicates or be able to produce extra parts and change and repair with time. But autocatalytic growth was something I didn't really mention, and this is the idea that you sort of get a feedback process. So you can see from some of the arrows that this is leading to self-assembly. And so what it really was saying that we need a morphogenetic process. And as we gather resources, then what ends up happening is you see like an increase on a catalyst, right? The idea is that growth will start to grow up to a certain point until, of course, you have no more resources. This is what we talk about, the niche. Providing that substrate, that material and energy exchange is really important. And of course, doesn't allow you to just keep growing infinitely. Ultimately, what this leads in cybernetics view is this another principle called the principle of recursive growth, which ultimately leads to the emergence of heterarchical, not hierarchical, heterarchical systems that are saying things grow really, really, really big. And of course, they start creating things that are stable in the sense of building blocks. So there's a point where a system that's reached like an ultra stable state or has reached a certain point of organization becomes a building block to a much bigger, higher level system. And so that's kind of where the idea that like Herbert Simon and other classical thinkers talked about emergence of heterarchical systems. So effectively, it's trying to say that you need to essentially build in these morphogenetic changes. You need to have this process that promotes growth and self-repair, because this is what's ultimately going to allow that system to continually persist over time. And again, it sort of affects that the idea is that you get more and more complex systems. I didn't mention it later in the talk, but you can have nested Markov blankets. You can have Markov blankets of Markov blankets of Markov blankets, and now you get the of top-down and bottom-up causal modulation. But ultimately, growth is just trying to say that we need these resources and we need to be able to replicate either your entire entity and then add mutation, which creates the offspring, as I mentioned earlier, or you need to be able to reproduce and grow and replace subsystems. And that's the part where the building block concept comes in. There's also one final comment that at least I recall, which is that as these things become stable, systems that are built of lower subsystems make it easier for those building blocks to join in, because again, now we have this organizational principle from a high level relationships between parts. I don't know if that was helpful.
Yeah, it was. Okay, thanks.
Yeah, thank you. It's a good question.
Anybody else?
Yeah, I also have a question. So one of the hallmarks of classical von Neumann computers is programmability, right?
What type of computer? I just didn't hear you.
Von Neumann computers, the conventional computers. It's programmability. So we can almost anyone can write a program almost using natural language. What about programmability of model computers? Do you think that we might need some sort of model programming language framework, which is fundamentally different from a traditional programming language framework?
That is a really good question. And yeah, that is something that, in my view, you would lose from classical computer, because the idea is that, as I just said, and everything is sort of dependent on the morphology and the niche in which that morphology is to exist and that agent or that mortal computer is to interact with. So I would say that it gets difficult because you need to now account for the properties of the morphology. And sprinkled throughout the paper, we talk about that the homeostatic variables, or the metabolic primitives, will largely depend on the actual substrate in which you are building. And it could be in silico, it could be biological. I think that there is potentially, and it's not clear to me how, so I'm just speculating, to design general specifications, not so much that it would be like you can program in a mortal computer just like you would in your standard von Neumann computer and like the Python programming language, but you could take advantage that the system's organizationally closed and that they have essentially relations between the parts. So there are some sort of design principles that they adhere to. And I think you could design some level of general programmability for certain classes of mortal computers. It wouldn't be like, oh, let's say I have an animal, or let's say a very low level type of mortal computer, something very low level cellular versus a complex organism. I would say that the programming specifications might be dependent on the class of mortal computer and the type of entity and even the niche in which it interacts. But you could essentially program classes or slices of mortal computer. So again, if we're dealing with like, I had in my other diagram, the neuro robot, and that was a version of like the dog robots that come from like Boston Dynamics. You could essentially imagine designing a programming language around those types of quadrupeds. And so I think it would be, you'd need to account for like the essential primitives and the environmental variables that are part of this process. And we need to be able to specify them to some degree if we want the programmability. I think it gets complicated though, because I do think while we are sort of arguing for this entanglement, right? Because the software really isn't divorceable from the hardware and real entities. The place where maybe you get some of that general programmability is in the virtual morphology. And I think that's our best bet, because ultimately when you're building these systems themselves, you sort of need to work with the actual hardware. If we're talking about, let's say, robotics, it's a little bit different with biological entities too. Although I know like the xenobots that you have or the anthrobots even, you have ways of which you can program them. And there was some biochemical processes that were described in some of Mike's work. I don't know if that helps though, but I do think you lose some of that programmability. But what you gain is this massive energy efficiency as you start to approach those lower bounds. You start to approach the place of thermodynamic efficiency, the best that you can get with physically realizable Bayesian inference. I do think, though, that the programming part can come in from more virtual morphologies to allow us to deal with the organizational properties and allow us to experiment and work with different designs. Does that answer your question to the